Previously, we talked about the roles of log and e in solving a general exponential problem. In this video, I want to give you a real-life example. One of the universal topics in almost all science is change. Once we observe how one thing changes with the other, we can find out one based on the other. The two things can be status and time, for example. So if we know how status changes with time, we can use that to figure out one from the other. For example, the relationship between distance and time. The simplest case is uniform motion, where per unit time change of distance is constant. In that case, the relationship is straightforward, and we can easily back out time from distance. But another common case is the exponential one, where the per unit time change is no longer constant. In fact, it can be greater and greater or smaller and smaller. It's typical when we're dealing with status such as population, sizes, amounts, and etc. But if you view it not from the absolute sense, instead in terms of the rate of change, then it's constant. Per unit time, it becomes constant multiples of the prior one. So we end up with the exponential relationship between the status and time. Now, solving this is no longer a simple division problem, but you need to divide the two logs. A real-life application is the carbon dating technique, where the amount of carbon-14 is used to date artifacts. It's invented by the American chemist Wheeler Libby. He won the Nobel Prize in 1960 for that. Simply speaking, these artifacts have carbon-14 atoms, which will decay over time. You can measure the speed of decay. Then the original amount will go through that decay for a certain time to become the final amount. So you can find out the age of the material as the ratio of the two logs. Of course, the tricky part is to measure the speed of decay, and also figure out the remaining ratio in terms of the original, because you don't know the original amount. Here are some more details about this technique. Let's start with where carbon-14 comes from. Cosmic rays enter Earth's atmosphere, and once in a while it collides with an atom, knocking out a neutron. This neutron might collide with a nitrogen atom. It has 7 protons, 7 neutrons. This neutron will kick out a proton and takes its place instead. So now it has 6 protons, 8 neutrons. It becomes a carbon atom, but a carbon-14 atom, with 6 protons and 8 neutrons, as opposed to the most common carbon-12 atoms with 6 protons, 6 neutrons. Plants absorb carbon dioxide through photosynthesis, and some carbon-14 will be absorbed. So living things, whether animals or human, because they eat those plants, so they also take in some carbon-14. But carbon-14 is not stable, unlike carbon-12. It will go through beta decay to become a nitrogen atom again by changing one neutron back into a proton. The rate of decay can be measured in a lab. It's measured that 1 unit of carbon-14 becomes about 99.9879% 1 year later, so the change is really small. But since we're also constantly absorbing carbon-14 through food, the amount of carbon-14 reaches equilibrium in our body. So all living things have a pretty much similar carbon-14 to carbon-12 ratio. Say it's 1.94 times 10 to the power of minus 18. But once that organism dies, it stops taking in more carbon-14, but carbon-12 stays the same. So now this ratio will go down. Let's say we found out that in this charcoal specimen, the new ratio is measured only 0.2813. Now comparing these two, we can find out that the amount of carbon-14 is about 14.5% of the original. So now we can find out the age of the specimen by calculating the ratio of the two logs, roughly 16,000 years old. So in this course, we've talked about what E and log are and their relationships. and we've also seen how to use E and log in solving an exponential relationship. In our next course on stock price modeling, we will explore their applications in modeling relationships. So stay tuned if you're interested.